Introduction to Eigenvalues and Eigenvectors. Now, in this section, we're going to be asking ourselves whether there exists a non-zero vector x, such that matrix A times vector x is just a scalar multiple of this vector x. And we call this the eigenvalue problem. So to begin, let's consider the following definition. We want to let A be some n by n matrix. Now, a scalar, lambda, is called an eigenvalue of matrix A if there exists a non-zero vector x such that the following holds true. So we can say that lambda is an eigenvalue of matrix A if the equation matrix A times vector x equals lambda times vector x has a non-trivial solution. In other words, a free variable must exist. Right? There's no linear independence here. Now, such a vector x is called an eigenvector of matrix A that corresponds to this lambda, this eigenvalue. And again, what we're asking ourselves here is whether or not there exists non-zero vectors x such that matrix A times vector x is just a scalar multiple of vector x, where lambda is that scalar. So let's take a moment now and think about this geometrically, or think about the graphical interpretation of this eigenvalue problem. Let's now explore a little graphical interpretation of this eigenvalue problem. So to begin, let's start by considering some arbitrary vector x in R2. Now, lambda times vector x is just a scalar multiple of this vector x. So since lambda is a scalar multiple, we know that it could stretch, it could compress, and let's give ourselves a little bit more room here, because lambda could even reverse the direction of this vector x. So we can see here that, in other words, if a non-zero vector x exists, when we multiply matrix A, that n by n matrix A, by vector x, this should produce a scalar multiple of that vector, where that scalar multiple is lambda. So let's go ahead now and explore this in more detail with some examples.